Last class we have discussed about the basics of an algorithm. Today we are going to look at the efficiency of an algorithm or the basics of algorithm analysis. Before we discuss about algorithm analysis, let us discuss about the efficiency of an algorithm. So, what is meant by efficiency of an algorithm? How long an algorithm takes to produce its result represents the speed of an algorithm. Okay, how quick it is in finding the solution for a given instance. We know that computers are not infinitely fast. It needs some time to do computation, and memory is not free. Hence, finding an efficient algorithm which requires the minimum time and memory requirement is important, because time is precious and memory is costly. So, we need to have an algorithm which is efficient in the sense that which is taking minimum possible time and minimum memory for its execution. And the important resources of a computing device that an algorithm consumes during its execution are time of the central processing unit, how much time it is taking, memory, how much memory it needs to store data and program, communication bandwidth. If you look at a networking application, then what is the bandwidth requirement, and depending on the application domain, other hardware resources. These are all important resources. And if there are two algorithms or two or more algorithms to solve a given computational problem, then you can define efficient algorithm is the one which has the minimum resource requirement, which minimize the total resource requirement. So, that is basically what efficiency means. Now, we can try to see what is algorithm analysis. It is the process of determining the resource requirement of an algorithm. So, before you execute, you can do it. It is called a priori estimation of the resource requirement. A typical case is determining the time requirement. So, given an algorithm, what time it needs for its execution, and for estimating the resource or time, we need to have a model of the computing device that we are targeting. In what kind of a computer the algorithm is going to be executed. We know that it could be a single processor computer, or it can be a multi-processor computer, and within a given processor also there are different kinds of processing. For example, a sequential machine which executes a sequence of instructions one at a time. That means you assume that our model is a single processor computer which do a sequential processing, meaning if you are given with a program of 100 statements, the processor is going to execute the first statement, and then after finishing it, it goes to the second statement, and it goes like that. Okay, that is sequential, as opposed to the parallel execution, where maybe you can execute more than one statement simultaneously or in parallel. Assume that our machine is sequential. I hope you are getting the model. And a typical analysis determines the result as a function of the input size. So, basically the objective of algorithm analysis is to estimate the resource requirement of that algorithm. It could be the time requirement, the memory requirement, like that. And typical analysis finds this result as an estimate on the number of input or input size. Then what is input size? It could be the number of elements in the input. For example, if you look at the sorting problem, the input size could be the number of elements in the list. Another parameter determining the input size could be the number of bits required to represent the input. For example, if you look at the algorithm for primality checking, that is, given a number, check whether it is prime or not. And it was not to be a very complex problem. People thought that it's an exponential algorithm. That means the time taken is exponential in the number of bits. But by a recent recent I mean in 2010, between 2000 and 2010, computer scientists from India, from Indian Institute of Technology, Kanpur, proposed an algorithm proving that it's not an exponential algorithm. So here the point is that if you look at primality checking, only one input is there. You can consider here the size as the number of bits required to represent that number, and hence you can obtain the time complexity or the time requirement as a function of the number of bits required that you need to represent that number. Okay. Sometimes input size may be represented by more than one quantity. For example, suppose you are looking at a graph traversal algorithm, then you may be interested in estimating the time in terms of the number of edges and number of vertices. Okay, so it could be a function of more than one factor, and typically running time is estimated in terms of the primitive steps, that is the basic steps or instructions to be performed to compute the result. And each primitive instruction is assumed to take a constant time for its execution. For example, if you look at the sorting problem, the most common operation performed is comparison between two elements. So comparison is the most fundamental operation. So for estimating the time for a sorting algorithm, you can assume that a comparison takes a constant amount of time, say C, and then you try to find how many comparisons are required for sorting. If you see that it is n comparisons, then you can say that the complexity or the time requirement is n multiplied by C, where C is the constant assumed as the time requirement for one comparison. And suppose you can find that maximum of n comparisons required for sorting, then n into C is the estimated time. I hope the basics of algorithm analysis is clear now. Now let us proceed. Now you can see by using an example how can you perform analysis on an algorithm. We are going to look at how we can estimate the time requirement of an algorithm, and for that what you can do is, as we saw in the previous slide, you can assume that a constant execution time Ci for each primitive statement I. That is, if you look at the algorithm, you can see that for a single statement in the algorithm, the time taken is a constant. For the ith statement, you assume that it is Ci, cost of I. Okay, for example, if it is an addition, you can say that okay, the cost of addition is say 50 unit of time, it's a constant, that's an assumption or an abstraction. This is one way of doing an algorithm analysis. Okay, assume that the time required for a particular instruction is a constant for a given machine. Then what do you do? Find the number of times each statement will be executed. It's called the execution count. So now you have time for each execution of a statement and the number of executions of that statement. Then the total time will be n into Ci. So then you can find the total time requirement or time complexity as the sum of products of execution count and execution time. For example, suppose there are two instructions, C1 is assumed as the time taken for first instruction and C2 is taken as the time for second instruction, and suppose that the first instruction is executed 10 times and the second instruction is executed only once, that is the first one is in a loop, second one is not in a loop. Then you can say that it is 10 into C1, 10 times the first statement plus C2, because C2 is executed, or the second statement is assumed to be executed only once. Okay, now you can consider our insertion sort for determining the cost of performing this operation sorting. So there are 8 statements. So you assume that C1 is the time for executing this statement, C2, and here is a comment. So not going to be executed, that is why the cost is 0. Similarly, you are assuming constant cost for each of these statements. Okay, and now you see that assuming that a dot length is n, number of elements is n, it varies from 2 to n, and hence the total number of times it is executed, this particular statement is executed, is n, because when n is a dot length, also it goes in and next time it comes back to the control statement again and goes out, so it is n. And inside this for loop, every other statement is executed n minus 1 times, and that is why this statement 2 is n minus 1, every other statement is n minus 1, and you have a nested loop here. So this while is executing within the loop, right? And now this Tj is assumed to be the number of times the test in this while loop, that is this condition checking, is executed. Okay, we don't know what exactly it is, so you take it as a function Tj. What is it? The number of times this checking will be performed for every value of j from 2 to n. That is what you are doing. Okay. So that is the number of times, and now if it is executed Tj number of times, then it is very clear that the statements within that loop will go for Tj minus 1 number of times. Okay. So this is the execution count for each instruction, and finally this is outside this inner loop, so it is only n minus 1 times as it is for the other statements in the loop. So that's it. And now what you do is the sum of products C1 into n plus C2 into n minus 1 plus etc. It's just a summation, you can verify it offline. Okay, this is the estimated time for execution when the input size is n, number of elements is n. Okay. Now maybe we can see what is meant by the best case algorithm analysis. That means in the best possible case, what is the minimum possible time? Here you assume that, okay, in the minimum possible size, this could be the best case where the number of times this particular condition check will happen is 1. So here is an example. Suppose you already have a sorted list like this and you are going to insert 120. Then only one checking is required. The first time itself you can see that AI, which is 98, is not greater than 120. So in the first time itself the check will fail and the control will come out of the loop. So this is the best case. Tj will become 1. Then what is the analysis? Tj will become 1 So, if you substitute, you will get this, these two become 0, and if you rewrite, and you can see that it's nothing but this constant. Okay. So, you see that if you rewrite, I am representing this summation of constants as another constant a. Okay. I am assuming that a is nothing but this sum and b is nothing but this sum. Okay. Now, you see that there are two levels of abstraction. One level is we assumed that the time for execution of a single statement is a constant. That is the first level of abstraction. Second, after obtaining this as the function value, so this is a constant, right? Sum of these constants, which is abstracted away with a single constant. You assume that a is this constant and b is this constant. Then it is nothing but a constant a into n plus b, which is a linear function on n. So, we found that the best case performance is linear in the number of input. Okay. Now, we can look at the other extreme, which is the worst case. What is the maximum possible time? So, for that you assume that maximum possible means the value of Tj can be j. Why? Because already you have j number of elements sorted. In the worst case, all these j numbers will be less than the number to be inserted. For example, here you have j is equal to 1, 2, 3, 4. So, all the 4 numbers are greater than 11. So, this check will happen for maximum of j number of times. So, that is the worst case. So, if you substitute, then this will become 1, sorry, j, and so it is actually sigma j is equal to 2 to n, j is this number. I hope you know this result, otherwise verify it offline. Anyway, what we did is we assumed that it's Tj is equal to j, that is the worst case, and in that case if you substitute the values, for the interest of time I am not discussing it, you can verify it offline. What I did is I just substituted in this formula Tj as j, then this is j minus 1, okay, and the summation is this value. If I substitute these values here and take the sum of products, I will exactly get this. After rewriting this equation, you are getting it as a constant into n square plus another constant into n minus another constant. So, you can say that it is nothing but a constant into n square plus another constant into n plus c, that is it is a quadratic function of n. So, we can see that in the best case it is quadratic, and in the worst case it is quadratic, and in the best case it is linear. And not that, we have two levels of abstraction. One level is we assume that the time requires for executing a single statement is a constant, and then we are abstracting another constant with like this a into n squared, and that is why I say there are two levels of abstraction. So, today we have recollected the basics of algorithm analysis. Algorithm analysis is the process of determining the resource requirement of an algorithm, and the resources can be the CPU time, memory requirement, communication bandwidths, or other resources based on in which system the algorithm is going to execute. And we have discussed algorithm analysis as an example to find the execution time or an estimate of the execution time. So, the basic approach that we discussed works as follows. First, it assumes that for every statement the time for execution is a constant. For ith statement it is Ci. and then the idea is to find how many number of times each statement is executed. If you estimate that, then the estimated time is nothing but the time for executing the first statement C1 into the number of times the first statement is executed, that is N1, C1 into N1 plus C2 into N2 plus etc. So, this is the basic approach. Given any algorithm, it is not difficult to find what is N1, what is N2, etc. Just look at where it is. If it is not in a loop, take it as 1. If it is a loop which goes from 1 to n, take it as n plus 1 for the condition checking, and for each statement in the loop it is n. Similarly, you can count for nested loops as well. And I hope you are getting the basics of algorithm analysis, which is the process of estimating the resource requirement for executing an algorithm. Thank you.